say it's recording. It's kind of cool, actually. You can see the microphone on here. See, it's got the little bar here. You can see input level. And of course, if I walk over here and keep talking, it's higher. That's like the maximum over the past, I don't know, half a second or something like that. And so yeah, I think we're recording this time, and I can read it, and I think this is gonna be good. I guess I can't quite see the bottom of the screen, but that maybe. I see you switched to webcam recording too here.
Yeah, well, I'm trying to make it easier.
Yeah.
I can get a better vantage point than you.
Yeah. Yeah, my vantage point's okay. It's not like ideal because it's on. Let's shoot this up there. See, is that better? Yeah, that's better. I still can't quite see the bottom, but actually that's partly a
Clip
camera
it onto
angle
mine
issue.
if you want. It'll get it a little bit higher.
Funny. I got it right there. I just hadn't turned. I've been trying to move it back, thinking that it was the angle there. What I actually needed to do was turn it a little bit. This video is going to make people seasick now. Okay, that's good. So screen over here. Okay. So let's see. The lab is I made it due by the end of the day, not the beginning of the day. And my thought was to start out the class with them using comments that were found in the code, but I've only got a couple so far. So I'll just put them together for next time when I have all of them, and I'll hopefully do better.
Well,
yeah.
there's.
Sorry, I accidentally labeled mine 440. Did you get the email I sent?
Oh yeah, but I missed that on my count of 2, so I'm actually at 3.
I sent mine in at like 11:30 or something last night.
Yeah, I have yours.
Okay.
Yeah, yours is amusing. You found ASCII art.
Oh, cool.
Yeah. So anyway, there's I'll just go over those when I have the full set. But so far people have been finding good stuff with that, and I'm glad it's been amusing. Just a reminder, just in case you're like, wait a minute, so is there something due today? It's lab 1 here, and it says due Thursday, September 3rd by the end of the day. That's today. So anyway, that's that. What else was I going to talk about? Oh yeah, C programming and function pointers. Kind of where we left off, really. So I might actually tempted to do a kind of a tangent here, because I believe I have a kernel module in here, and this is actually part of a lab assignment at some point. But I just saw it there. RW.mod.c. Okay. So when you write one of these kernel modules, what you end up doing is basically writing a couple of functions that are pretty simple. That was the info file. Let's look at this one instead. So in this case, we got a file that we're making in a proc file system, and we've got a read function and a write function. And so all this kernel module really does is make this special file, and then you can see that these functions work. So it prints out in the kernel log that we read things, and it's got an init and a cleanup down here too. So when we get these structures, you can see we got this filp thing, a struct file, and so inside that we've got a file path and a dentry, which is directory entry, and we've got a name, and yeah, you can see all of this stuff in there from that structure. Okay, so we end up getting this structure, and we go way down through it and find stuff. And that's going to be a common theme in most of these kernel modules that we're going to end up making at some point. Okay, I thought I had one more in here that did stuff with the lights, the keyboard lights. And let's see. This is things that end with C, and apparently the cache is like a big source of things that end in C, and so is this video game here. So I'm just using all the same things that I showed you a few days ago.
What's PyC?
PyC?
.pyc.
Oh, it's a compiled Python file.
Oh.
Python will half compile stuff, and once that's been done, it can run a little bit faster than it would before. Okay, I got this mnet thing, kih.c. Okay, here's a keyboard handler that basically reads, or excuse me, a kernel module that reads keyboard scan codes. And so we got something here that handles scan codes. And so we're going to initialize the module down here. And for that, we have to request an IRQ. And notice right here, we request the IRQ. This is requesting that we be notified when an interrupt is made. When the CPU is going along, gets interrupted by something, in this case, the keyboard. Maybe that's harder to read now that I highlighted it. But basically, this is a void pointer to an IRQ handler, which is this function right up here. Now, the whole void star thing there, for a lot of these callbacks, you don't necessarily know what type you want to use. At least when the kernel was developed, they didn't know what type we wanted to use. And so if we want to support a variety of types, then the void keyword allows us to do that. Because you can pass a void pointer, it's just a generic memory address, and then you can change it to whatever you like later. Okay, so that's an example of passing a function pointer into our IRQ handler, which is going to get used later. Oh, so today I want to talk more about function pointers and actually put some in a structure and that kind of thing. So I kind of skipped the whole drawing the stack on the board. I do want to point out something about function pointers here. Let me make a demo to illustrate where we're going here. I'll do this in the class examples area. Okay, I'll call this return function.c. Okay. So we got a main function there. I guess we'll return 0. Okay, so that's our basic C program. So I'm going to make a function in here, and it's going to return a pointer. So return pointer, and I want to, well, I'll give it a parameter. Why not? A number n. Okay, so inside this function here, I'm going to go ahead and make another function. And this function returns an integer. I'll declare an integer in here too. But let's make a function that returns one. Okay, I'll call it count. And it doesn't take any parameters. Okay, and count returns C++. Okay, and I'll make an int c here that starts out equal to n. Return count. Okay. And count there is a function. So if you remember from our types last time, what we ended up having here is like int, count, well, or whatever the name is, pointer to count, whatever, int, if we wanted to specify the complete type here. But instead of doing that, we're going to return a void pointer. And that way we can return whatever memory address we like. So down here, we'll go ahead and do a cast. There are casts from like CS250 or somewhere. Getting dubious agreement here. Okay, what a cast does is inform the compiler that we are going to change the type of something from one thing to another, and it doesn't do any type conversion at all. So one thing you could do with a cast, you could say, okay, we're going to make some kind of an integer, int a. And we could say we're going to have an unsigned int b. Okay, well if you say b equals a later, assuming they have values, then that's kind of a type mismatch here. And so if you wanted to inform the compiler that this is going to be okay, you're going to take a and you're going to acknowledge that it's going to become unsigned, you could go ahead and turn it into an unsigned int with a cast, like this. But the cast doesn't do any conversion. So, this kind of situation here, I mean, that works just fine. If you got something like this, then you're just going to inform the compiler that, okay, the 32 bits that represented this float are now going to represent an unsigned integer. And they're not being changed, nothing like that. You just take those bits and start pretending they're an integer. So that's what a cast does in C. And so when you make a cast like this, we're saying, well, we're going to say that the type of this thing count up here, which is that function right there, is going to be a void pointer, a memory address. Okay. this whole thing is coming through here, so we can say void star count function equals return pointer 5. Okay. And this is going to make a little bit of a mess here. Okay. So I'm going to go ahead and cast this thing as an integer pointer, so we can actually use it. Okay, so that's going to be an int, or excuse me, a function pointer. Well, now let's go ahead and do it. I'll call it a count function pointer. Okay. And that takes an int and equals count function. Okay. The compiler would be justified in giving us a warning right here, because we've taken something that's a void pointer, just a generic memory address, and assigned it to something with a specific type. Let's go ahead and call it. Okay, and CFP. Okay. Call it a few times. We're going to have to set GNU99, so use a nested function. Okay, too few arguments to function CFP. Oh, that's because I declared it wrong. Nobody mentioned that. It doesn't take any parameters right here. So I can't take any parameters down here. And indeed, I didn't give it any parameters down here. I also made a mistake here. I have a percent sign S. That's a string. We don't want that. We want D for an integer. Okay, so both of those things fixed. Let's try that again. Compile. Okay, so at first we're fine. We got a 5 there. And so if you look at count up here, now we got count C++. So we're taking the value of C, which is 5, and we're returning it, and then we're increasing it up to 6. So if you can see this thing's running. If we say C plus 10 up here or something like that, then we should get 15. And we got 15, and then we got our segmentation fault. So here's where the segmentation fault's coming from. And this is something where you got to be real careful when you're doing this kind of function pointers from one place to another kind of nonsense. So the stack builds from the top of the memory space. And so we got a stack frame up here for main. Okay, then after that, we have a stack frame for our function over there, return pointer, what do we call that? Oh, I can't even see that in the camera. I'll do that, I'll do that. It'll be nice to our remote viewer. Hey, I can see it, sort of. Okay, so this is our other function up there, return pointer. Okay, so when we call that function up there, we're creating inside it basically another function here called count. And then at the end of it, we're returning a pointer to count back up to main here in this count function. Okay, so when in main we call this function, it works fine the first time. Because the first time it's just sitting here in memory. But it's not safe in memory. This stack frame has been deallocated. Return pointer is finished running. And so this area here is available, and the next time we call a function, it's going to get overwritten. And that happens as soon as we call printf. This will happen first because we got this function call here. We need the value from it, and then we can call printf. And then after then this has been overwritten. We try and call count again, and it doesn't work because the memory contents have been changed. Okay, so we go back to all the way just on screen configuration. There we go. Oh yeah, I see you're turning yours there too. Okay, so over there on this thing in here. Incidentally, let me show you one more thing. Okay, I changed this thing up here to be C++ again. Okay, and down here, well, we'll make a few variables. Int A, B, C, D, E, F equals, well, if we do that, they're all going to be the same. Okay, and I want, the thing came back, CFP. Okay, B, C, D, E, D. Oh, I didn't do F. I guess I didn't really need to do that many. 4, 5, 6. A, B, C, D, E, F. Okay, so we call it 6 times in sequence here. Take a look at what happens. Okay, compile that, run it, and we get 5, 6, 7, 8, 9, 10. So you can see it actually works just fine as long as we don't call another function and overwrite it, which of course we shouldn't do. So this isn't really a good way to do things here. If you wanted to return a function from a function, then the way to do it would be to declare count somewhere else. Actually, let me rip this thing apart and fix it in a different file. Return function fixed. Oh. There we go. Okay, so we take this count out and we put it up here like a normal person. Well, normal depending on the language. And then in here we make it static in some sort, or you can make a global variable. That would work fine. And C up here, and down here we just say C is n, and return a pointer to count. Then let's go ahead and compile that. Function fix.c. And you can see it works this way. And if we change this so that we're doing it the original way, take me just a moment here. Okay, nice that in. Okay, see if. Okay, that will work and see. Okay, so this whole business with not being able to return a function, it was dynamically created inside a function. This isn't necessarily a huge deal, probably. I mean, it's not the kind of thing that, maybe it's the kind of thing you do every day. I don't know. I use that feature semi-often because a lot of languages have it. So these, I want to talk about static versus dynamic scope. It's irrelevant. I don't have time. Okay, I was going to if I had time. Maybe later. Okay, so first-class functions. In order to have first-class functions, a language has to be able to basically treat a function like a variable. And I showed you we can store a pointer to a function in a structure, or pass it around, or return it from a function. That's all good. But what we can't do is create it inside a function and then return it from that function and have it continue to function properly after that. And so that's really the main thing that's missing here from true first-class functions. And so anyway, yeah, I've showed you that one, showed you that one. Now, a lot of languages do have that ability. Python, for example, you can create a function inside a function and then return it. Okay. So, Python. Yeah. Okay, so in Python we can say def return function, and then inside here we can make a function. I'm just going to make a pure function here because actually it won't work if I don't, which is a slight weakness in Python here. Okay, and what am I doing with semicolons? I don't know. Okay, there equals return function square 5. Okay, so we created this function inside return function, and squares things. It doesn't have a name until we get here, and it's stored in this variable. Okay, did it print it out? Yes. Okay, so we created a function inside a function. Now, you might like this to be like, well, wait a minute. We also had this variable C, was it? That was inside here. Well, that doesn't really matter. It's still going to get overwritten when you call another function if you do this kind of thing in C. Okay, so that's a problem. If you think about it, in order to support this feature, the function, the code for it, has to be stored somewhere other than inside this this stack frame where it was created. And yeah, certainly that can be done. Okay, not a big deal. C++ 2011 supports anonymous functions, lambda functions. So you can do that in C++ 2011 if you like that feature. Okay. Oh, can a function take itself as an argument? Yeah, probably. Has to be done carefully. Obviously, this will be recursive, like, but in a weird way. Okay, oh, good boy. It'll be easy. Okay, it needs to take a function. There's two ways to do it. We could just say void star and then cast a later, or we could specify the whole thing up here. It's going to take itself, so self. And does it take any parameters? Uh-oh. You know what type parameter it takes. And so on and so on. Let's just use a void star. Because otherwise we're going to have kind of like a recursive definition here in terms of what we're trying to pass in. Because what we're trying to say that we're going to make a function and it takes a parameter of type, you know, a function, it takes a parameter of, you know, the type we're trying to describe here. So it's going to be like the point in the camera at the screen thing here, trying to describe what type this takes, unless we use a void star. Okay, and okay, so first order of business here, let's make self into something we can call. That's fine. Okay, what's it take? It takes a void star. See, we solved our little recursive pickle here. Okay, so now we've got something we can call, and certainly we can do that. And let's go ahead and print something out here. Okay, we'll print out the address of the function we received. Infinite recursion. We gotta stop this at some point. Okay, there we'll stop. And let's say what stop is too. I realize I just made a global variable to stop a recursion, which is not the ideal way to do it. We can fix it if you really want to. Okay, no declared here. What do we do? Self. Oh, I call it self function right here. Straighten the names out like this. There we go. So there we go. It's kind of funny the way the I think I did something funnier. Oh, there, I put the new line there. That's it. That should look better. Okay. So we have a function that takes itself as a parameter. If we want to stop it, you know, the conventional way, we could say like int stop here, and not bother with that. And then here we'd say self foo stop -1. We wouldn't bother with that. And I feel like I just deleted a really important line.
Do you have nothing declaring what self is?
Yeah, you're right. It was this line right here that I killed.
Bottom.
What's that?
Just saying if the declare stuff down when you call it down at the bottom.
Yeah. I'll have to say foo and can. Oh, and right here. I think I did it right that time. There you go. What use is it? None. It's illustrating a point. I don't think I've ever seen this type of recursion done, and it would be kind of silly to do so because you can just call the function from inside itself. You don't need to pass the pointer. But I just want to illustrate here that these function pointers are quite generic. You can do whatever you like with them. And There's not some particular limit where the compiler is going to say, no, you can't do this. No way. There's sometimes it can be hard to say what you want to say. We ran into a thing up here. See this type right down here, void star. If we weren't using a void star, and we were actually including the whole type, I think maybe I lost everything when I said this before. And we'd have to say something like this. And the thing I would say right here is kind of starting over on this whole thing, because the type it would take first is, of course, a void, whatever. So you see where we're going with that. So that's why the void star saves us from the whole kind of recursive definition nonsense. And but casting something like this inside your function is really pretty common anyway. Let me show you something real quick. The way that you make threads on a C program, or at least one of the traditional ways, there's about maybe 4 different ways you can do multi-threading. But one of them is using this pthreads library. And this function here creates a new thread and starts it running. So it takes this void star, start routine void star. And so this is your function and it's going to go run. So that'll start running on another processor and has to return a void pointer and take a void pointer. This void pointer here is your parameters. This is your one shot for all your parameters. And they get given to whatever this function is that you're going to run using the pthread. And so you get exactly one parameter, but you only need one because your one parameter is a memory address. So you just have to store any parameters that your function needs in such a way that you can get to them from just one memory address. Popular way is just put them all in a struct. And so you give a memory address to that struct, and then you got everything. So that's just a typical use of a void star. In this case, we didn't void star in the start routine. We're void starring into parameters. And you can actually have that void star back afterwards if you want it. But anyway, so the pthread works like that. Sometime in
So the arguments is optional?
Yeah, you can pass a 0 if you want to.
Okay.
But
we have to put something in there. So
yeah, yeah. You can give it a
if
0.
your structure stores the arguments, then you wouldn't put anything in there, is what you're saying, right?
Well, if you give it when you run this, it's going to call some function you wrote. And so that function you wrote should take a single parameter of a void star. And if you didn't need any parameters at all, you can just pass it a 0, and you're still going to get a parameter when your function's called,
right.
But it'll be a 0 that you just ignore. But if you pass the memory address of a structure that, say you wanted 10 parameters, just make a structure with all your 10 members, pass a pointer to that as a void star, and then once you receive it, you cast it as your structure, and then you got all your information you need.
How do we build the structure then with the parameters in it?
Well, you just have to build it before you call pthread create. So if you wanted to do that, you just have to say, struct whatever, and then you'd have all these members, whatever. And so then when you're calling this in your actual code, you just go ahead and make your structure. Struct s, and like s dot a equals whatever you want to make it. And then when you call pthread create,
You pass S,
yeah,
pointer to
you
S.
got all that stuff, and then you got your
Well, S is a pointer to begin with. So,
right. So it'd be like not if you.
So you want to dereference it, or do you want to?
It depends how you did it. If you made it using malloc and dynamic memory, then you just want to pass X as a pointer. If you just made it in the stack, which is probably fine, depending on the exact circumstances, then you do want to dereference it.
Okay.
Just want to make sure you get a pointer to it somehow. Yeah. Yeah, so void star all over the place. Okay. So let's see. CDML return counter. Hey, I already did that. Cool. How to the stack, etc. Okay. Making a struct. This is just kind of putting everything together at this point. So if we go to user src Linux, or Linux source, let's go to 3.16. There should be a bunch of examples of this. I'll just go to our export FS example that we were looking at before. Okay. So you got this struct export operations, and it's got this set of members here. And so we're starting this out with just struct, and then we're declaring what our struct name is. Okay. I'm going to set up a second terminal in here. CS for okay. So if we're going to make an example, I'm going to do that. Well, I should do the traditional object-oriented one. I was debating which way to do it. Okay. Usually when object-oriented programming is taught, for some reason, we're always tempted to use animals and have objects that represent animals. I don't know how this got started. That's how I learned object-oriented programming, and that's how I always teach it, and that's how I've usually seen it done. The exception was when people try to use like database terms like records or whatnot. Occasionally somebody will think of something more creative. Anyway, so we got this structure.
I learned it using fruit.
Fruit? Oh, really? Okay, that's a good one.
Yeah.
Is that here?
Yeah.
Oh, I shouldn't have copied that.
He doesn't teach here anymore. So.
Oh, okay. Well, he's from far away. Maybe they do fruit there.
Yeah.
So I got this struct cat, and so I'll make a function here. Okay. Okay. Yeah. Okay. And just take the parameter. Sure. How many times? Okay. And so that's basically following this whole form over here. Now, this function here in code FH, this takes a struct inode pointer for this first parameter, and then the next one's a pointer to an underscore U32. So we got a little bit less common types here, but the essence of it is something like that: function pointer to a something like that. Okay, and I'll have something like
Is U32 an unsigned 32-bit?
yeah.
Okay.
Yeah. I don't know why they want a 32-bit specifically there. I don't know the details of the file operations handling, but yeah. They're sometimes specific about bits in the kernel when it's something where like on a file system, for example. If you took your memory card and you took it out of a Raspberry Pi using a 32-bit ARM processor and you stuck it into your 64-bit machine, you don't want to upgrade the values inside the file system to 64 bits.
Right.
So sometimes it's pretty specific on the file systems. Okay. So let's see. I want this one to be void. It'll return a int. Okay. And this won't take any parameters. There we go. Oh, let's include some data. Sure. Okay. And so then we can write these functions later. We'll make an actual instance of it, and we'll make some implementation for these things. And so I'm going to say void meow, and I'll give it int time, and this will be a super simple one. Okay, simple function. Let's go ahead and implement hunt. Okay, so we'll say that it's going to return something. We'll say this return is whether it was successful, 0 or 1. And so in order to calculate this, we'll say if weight is less than 10, return 1. Because my cat is less than 10 pounds, always catches things, and else return 2. Now this is not really a very fair estimation of cats because some cats are supposed to be large. I just have 2 cats that are supposed to be small, and one of them is small and the other one's large. And when the large one goes out, she doesn't drag anything back, but the small one does. So there you go. The small one can jump about 3 times as far. Okay, so here we'll go ahead and make a cat. And let's take a look over here at where this thing was used. So, direct file operation. Okay. Okay, there's a whole bunch of places it appears as a parameter. Final operations. Okay, a whole bunch of places that appears. Try const. Okay, we're doing a little bit better there. Let's go to FS. Okay, now we're doing much better. Let's go to XFS. Now we're doing great. Okay, so XFS is a file system that's reasonably common here. Let's go down to the bottom. Maybe it's there we go. Okay, so here's an example of actually filling out one of these structures. And so the structure is created here. And you struct, and then you have its type. And then you have the name for the specific one you're making. That's my parents' cat. That is one of my cats. Okay, and then you have a, you fill out what the members of this thing are. Okay.
That's not cat.kiki.
No, there shouldn't be a period there.
Okay.
Because it's a structure of type cat.
All right.
And then Kiki is the name
Is
of
the
this.
name of the structure.
Yeah, exactly.
Okay.
Okay, and dot weight is she's a light one, maybe 5. Okay, and so then we can finish it that way. Okay, so we just basically mimicked all the syntax over here. Yeah,
You leave a period after your comma and then a semicolon.
you're right. That should be better. Okay. Let's try it.
Don't we need to pass a number of times to meow?
Oh yeah, good point. Yeah, that's good. So meow is yeah 4. Okay. I'm seeing other bunch of stuff here too. Implicit declaration of printf and such. Well, yeah.
You haven't
That's
included standard IO.
Yeah. Okay, I see I missed a semicolon at some point. Look at that again.
You might
Okay.
run it again, that printf might have thrown off other stuff. Nope, still complaining
So,
about the
10-1.
weight.
It's throughout the line now. Oh, right here.
You need a then after the if?
Didn't I put else? Yeah. So then, let's see, 16. If weight is less than 10, and hunt, let's say. Weight undeclared. Oh,
Yeah.
well, yeah. Yeah, it actually is.
You got weight as a structure up there too, so.
Yeah, weight is included in this struct cat, but in this function here, it's quite unaware
You can-
of what
right.
exactly that is.
Right, so we need another function for weight.
Well, weight is intended to be some data that's stored in here. And so we have to arrange to get it into our function ourselves. So this is kind of manual as far as the object-oriented programming goes. Not that you didn't realize that when we started putting into functions by themselves. But let's go ahead and pass this thing in. Okay. So down here, when we call hunt, well, let's see. Hunt is going to have to take an int weight. And so I'll have to change that up there. And this is going to make hunt a little harder to call, but we'll do that in a minute. So compile this thing. Okay, good. So,
Can you just explain what you did there again? So you changed the declaration of hunt
yeah.
to include a weight,
Right, so here's how we have to call it now.
and now we're, okay.
Because we don't have any automatic method that will give us access to our object. The other thing we could have done.
Seems like a workaround to why we weren't able to enter the weight into the structure.
Yeah. We could have entered struct cat us and or let's do stuff. Let's copy Python. Okay, somebody should be able to say self dot, well, probably want us to do it pointer here. We'll copy the whole thing. And so then we would say, like that. And so we can check and see if this, if we run this successfully. Oh, 0 for failure, not 2. There we go. See if it compiles. Not quite. Initialization from incompatible pointer type. Did I change something? Yes. I forgot to say struct cat up here. Which is going to bring us into a new amusing pickle.
Because it's a structure calling a structure.
Well, it's not calling a structure. So I got a successful hunt. Here's the amusing pickle that our compiler actually helps us out with, and so it's fine. We said struct cat star. We're busy saying what a struct cat is.
Right.
So it's taking one of the things we're still talking about. Luckily, that's fine. So this is the reason I changed it to struct cat star self is I made it wanted to make it kind of Python-like. So suppose we're doing object-oriented programming in Python. When we're inside a method of our object, we would have a pointer called self that lets us access our current instance of the class we're calling the method on. Remember that?
Right.
Okay.
That, yeah.
Yeah, so we just did it manually. And actually, on a Python function in an object, on a Python method, the first parameter that your method takes is called self. So
It's
we just
defaulted even.
yeah. So we've just done that. We just did it manually. So we got this this struct cat. We have to actually fill out the parameters here when we create an instance of it in order to make sure they got excuse me, not parameters, members, structure members, data members, which are actually pointers to functions. So we fill these out when we create it, and then if we want to call it and give access to our own data, we do that. Now in the kernel, it's rare to see data mixed into a structure full of file pointers. Notice over here, all of these things are function pointers. None of them are data members. And so it's not normal to see data members in here. I want to illustrate you can do it, show you the connection to object-oriented programming, but now I'm about to tell you nobody actually does it, so there you go. Okay, so that's manual object-oriented programming in C. C++ gives you the ability to do this in a more syntactically graceful manner. And that's the main improvement of C++ over C. There's some other changes there too. And actually you can write a C program that won't compile in C++ and vice versa. But the major difference is object-oriented programming. Okay. I think I want to go back to my old layout here. Okay. And got that. Don't need that anymore. Let's go back to notes. What am I supposed to be talking about? Okay. So structures. We made one of those. We didn't pass it anywhere. Well, yeah, we did. Well, we could pass it somewhere else too. How do you do that? If we wanted to, we could pass a cat to some function. So I can make some function here. Void use cat. Okay. Cat star. The cat. Okay. And how do we use a cat? I don't know. I just make a hunt. Yeah, it's already a pointer here. Okay, and then we meow it a few times. Okay, and then maybe we make a hunt again. Okay. So we can call that down here if we want to. I'll put a row of asterisks so we can see we move on to something else. Okay, and then call that one. Address it. Okay. There we go. We forgot to say if the hunts were successful or not. That's fine. You get the point. So we can take a structure full of function pointers and pass it to a function, and then we can use the function pointers in it, and that all works just fine. Okay, any questions? Does that make sense? Okay. I don't know. I'm not hearing resounding approval in that, whether it makes sense or not. Let's take a look at this this project real quick again. 430. Okay, so there's this project 1 here. You get these files, and I'm hoping that they make a little bit more sense this time. I think I actually have mine here as G1. Okay. So there's a struct bundle struct here, and takes it holds 3 function pointers: find best, sorted, copy, and combine. And you can see find best up there takes a void pointer, int, and a size t, and yeah, so you can read off the you can see the parameters for each of those. So if you're going to make a function to go into one of these things, I know what the parameter list looks like. In fact, if you cut and paste this thing and took off the parenthesis and a star and then the extra parenthesis there, you'd have a function prototype for it. It doesn't include any names on these things, and that's fine. Tester.c contains a file here that takes a pointer to a bundle, and then it does some tests on it. So it calls find best here, which takes a function pointer evidently here, and does some stuff on it. There's descriptions of what these are supposed to do in the project description. And the same thing for each of these others. So the bundle needs to come in with 3 callable functions, and test will call each of them in turn and do stuff in them. Okay, and so you can see there's a find best. It explains what each of these are. So the first parameter is actually a list of functions, and second parameter is for calling functions from them. I think I'm in an array by a list here. They're the same thing in Python, and so our terminology gets loose here. So the sorted copy basically does sorts copy something. I didn't read it and figure it out. Okay, so that's just about everything covered in some sense that you'll need to go and try this thing. The last one I haven't really talked about is these bitwise comparisons. Because bitwise comparisons, bitwise stuff, you got these operators here. You can do an and, an or. XOR is a caret. Or is a vertical pipe, single one. And is a single ampersand. And then you got shifts that shift all the bits to one way or the other, and tilde, which does not. So, in terms of doing these things, these can be kind of handy if you want to manipulate particular bits and get them all set correctly. So if you got something and you want 1100, and this is the current status of something. A lot of times on a device, like something in your computer, a sound card, network card, something like that, they'll have control registers. And the control registers is basically the equivalent of a bunch of switches. And so you have to send it the correct pattern of 1s and 0s if you want to turn the right things on and off. So each of these things will have different meanings. And so if you want to change what it currently has there and turn off, say this one, and turn this one off, what you can do is take this whole thing here and it with 1, 0, 1, 1. And what will happen here is you'll get a 1, 0, 0, 0. And so whatever you had before is the same except for this one particular spot here, which changes. Because these aren't both true. And so if you had something else in this register, say something like a 1 here, you're going to end up still having a 1 there. So AND gives you the ability to turn off particular bits inside your number.
So bitwise ignores the carried, if I remember right, the carried, because when you add 1 and 1, you get the carry of the 1 to the next spot, right?
Well, bitwise AND doesn't have anything to do with the carry.
Okay.
Because
we're not adding them, we're comparing them.
Right, exactly. Yeah. So that's what the AND does in that case. The OR does kind of the opposite. Suppose you wanted to turn that one on. Suppose you had like 1, 0, 1, 0, and you want to turn this one on. You do is OR it with, so OR is kind of a vertical bar like that, with a 0, 1, 0, 0. Okay. So in this case, if you think about truth tables here for a moment, well, this is this one or that one, so they come out the same. In this case here, this one is true. It doesn't really matter what that one is. The result you're going to get here is a true, right there. And if you wanted to change its state, well, that's a little trickier, because the XOR doesn't come across here right. What you might be best off doing is figuring out what the state is first. Because suppose you want to know if it's on or off, you just want to know. So what you could do in that case is basically just check to see if it's on. So here's how you check to see if it's on. Use your AND again, and this time use 0, and then for the one you're checking, you're going to check this one. I'll put a 1 in there, and 0, 0. Okay. So all these ones where you did a 0 are going to be a 0 every single time. If this one's 1, you're going to get a 1 there. And this number here is not 0. If this one up here was a 0, well, 0 and 1 gives you a 0. And in that case, this number is 0. So that's how you would check something using these. You check to see if one particular bit is set using these binary operations. So the last time I wrote a device driver, I should have stuck the source code up here. It would have been a perfect example. I believe I have it though, so I'll just show you real quick. I had it in that folder called posterity. It's DAS stuff. Okay, it would be harder than that. Fine. It'll be a hassle to find. I might find it and show it to you at some point anyway. The device I was trying to control was this audio sampling thing. It would take an analog signal in and produce a digital sample. It didn't have to be audio. It could be anything. But it had a bit that would start it from sampling and start sampling and stop sampling. And so a common thing to do is to read the device's control register and then do this process to turn it on or off or check or see if it was sampling, one of these three, and then write something back. So if we wanted to start a sampling, I check and see is it already sampling by reading it and checking to see if this thing's on. And then if it's not sampling, so it actually really does need to be started, then use an OR to go ahead and make the change happen, basically change it to a 1, and then write back to the device's control register. So it's like think of it as like a row of switches. Okay, so this row of switches approach, this is real common in controlling devices. It's also used in a lot of cases for encoding information really small. If you're in a networking class last semester, a lot of times we talked about protocols and using a binary protocol to save a whole lot of space. And in that case, a lot of times there'd be a header on the protocol. And I'll just grab an example real quick. That way everybody can follow, not just people over a networking class. Okay. TCP header, images. Okay.
You put in ICP. Did you mean to put in TCP?
No, I didn't put in TCP. I was bad at typing. They're not even close together.
Yeah.
Okay. So here you got this header, and I'll view image and make it big. It's got some numbers that are just integers of 16 or 32 bits or whatever. But here you got flags, and so this is basically 6 bits that can be used as switches. If you look from like here to here, is 32 bits. So if you're trying to process this thing, one thing you might do is take this whole thing and make it an array. And you can make it an array of 7 well, the data varies and options vary. Make an array of 5 integers and put the whole thing into it. So that's an integer, 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 integer. And the source port and the destination port, those are only 16 bits instead of 32. But you can get these things out using these operations if you want to. One of them is going to be easy. Depends on if you're on a big Indian or a little Indian machine, which one's easy. But you just blank out one of them using a and, then you got the other one. And so that'll get you one of them. The other one you just have to divide by 2 to the 16th power. So then this stuff right here, if you want to pick out a particular flag, you just have to use the right binary number there and use an and you can figure out if flags are on or off.
So you check each flag against that particular field?
If you're interested in it, yeah. If you want to figure out what a flag is, then you just need to have zeros straight across except for where your flag is, and it together, and you'll see whether your flag's on or not.
Kind of like looking at file permissions, too.
Yeah. File permissions in Unix do exactly the same thing. And usually you just, on the file permissions, instead of like 32 bits, you've only really got 3.
You got 3 bits.
Yeah, and you can check 3 bits in your head. You can be like, okay, well, I want a 5. That's a 4 and a 1, so that's 1, 0, 1. You don't think of it that way, though. You're like 5, okay, that's a read and an execute.
Right. But if you wanted to check to see if a file was executable, then you could look at the permissions and XOR that, or not XOR it, but either bitwise compare it with some string that you're looking for and see. Okay.
Right. And they actually put this in order for these groups of 3.
Yep.
So you got read, write, execute. Executes 1, writes 2, reads 4.
Right.
And so yeah, I mean you can do it in like in text or binary.
Right.
So like a representation of a
Because
bit.
you can do
using
bitwise comparison of characters too, right?
Yeah, you could. But remember that it's probably actually storing this using 3 bits, 3 bits, 3 bits, 1 bit. So it's 10 bits, which is not a standard amount. So maybe it's allocating 16 or something. But it's probably not allocating a character for each of these things in the file system.
No.
Because an R is 8 bits where you needed 1. Okay. So that can be used for setting these things. The shifts. These are used a little less commonly. This means all the bits scoot over 1. And so that can be used if you wanted to go through this thing and say you want to get rid of part of it. You can shift it over so that part goes off into oblivion. Or you can use it to increase the value. These are used a little bit less. Note that these are also the same as the insertion and extraction operators in C++. Like if you were doing like cout and inserting something into it.
So when you do a shift, can you add zeros as you shift so that it gets bigger, or are you just shifting, or you're restricted to the space that you were looking at, and then if you shift that all the way
I can make it
4
bigger.
characters,
Here.
then what are you filling that space with as you shift it?
Let's make a program here that shifts stuff around. Okay. Okay, so I'll make our thing to be shifted, and I'll just go ahead and make it a 15 to begin with, and so we'll print out 20. Okay.
And don't forget to cast.
Cast.
Yeah, because you just have A, you don't have to declare it.
Oh.
Or anything.
Oh yeah, the data type there. Yeah, sure. Okay. So we'll take we'll print it out. For instance, A shifted by 2. Okay. And I want to do it the other way too. Okay. Okay. So we started out with 15 there. I'm gonna go 16 instead. I got too many ones in that. It's easier to see what's going on this way. Okay. So we started off, we got 16, 64, and 4 on these things. So this one gave us 64, that one gave us 4. So if we look at where this stuff is going, 16, lost my pen, is 1, 0, 0, 0. And so then we went ahead and shifted it over 2 when we did that. And so then we got 1, 0, 0, 0, 0, 0. And then when we did it the other way, shifting it the other way, same thing happens.
Right.
Just go the other way.
So it inserted zeros as
Yeah.
we shifted.
Exactly.
Can you specify something different?
No.
Okay.
We can send it off into oblivion if we want to.
Right.
Let's go shift it like
Like
10.
10, and then it becomes bigger than the,
Becomes 0.
right.
It doesn't wrap it. Yeah.
Well, that's probably good, because then you could actually access different memory locations by shifting outside the register.
Well, yeah, I mean, if your 1 went off the end and then appeared 32 bits over here,
Right.
that might be fine. But
You could overwrite, yeah.
yeah, it doesn't go in a circle like that.
Right, they restrict
Yeah.
it, yeah.
Yeah. Yeah, so that's those things. Totally. Hey, I like to get this down here. Okay, percent 70. Okay, totally A. Negative 17.
So
Let's
shifted
make an
it.
unsigned. That'll be a little bit more obvious. I should actually have it print out and unsigned. I'm going to make it up and sign it there. Okay. This is the maximum for a 32-bit integer accepting the 16. So if we were printing out the maximum for a 32-bit, it'd be 16 higher. So here's what we're doing here. Not flips them all. And so if we had, I didn't bring my pen again.
Like a
0, 1, 0,
32
0, we'd have 1, 0, 1, 1.
Right, because it just flips them.
Yeah. So almost all of the 32 bits are on. I had the 16 off. And that's why when we did when we forgot to do the signing, we got negative 17. That's related to that one that was off.
Now with IP addresses, don't you do like one's complement to determine like the net mask?
Oh, yeah, yeah. Well, the net mask, you can basically go along and do the same kind of thing we were doing, block out part of it. So if you take a net mask of 255, 255, whatever, those are all ones. And so you basically block off of those from, yes, it's kind of like, doing the opposite there. Okay, so what else we got? That's about it. Okay. Any questions? Does that make sense? Everybody's nodding about now. So the bit shifts were easier. Okay. Just curious. Okay, I kind of skipped this whole dynamic versus static scope. I'll explain what the note was about. Dynamic scope means that as your function pointer moves from one place to another, the names inside it change in terms of what variable they refer to. This is not a common way for languages to work. PostScript works that way. You usually don't write PostScript, you just make a PostScript document, but it's actually a language. It's a stack-based language. Anyway, so static scope means that when your function is created, like in this particular case here, any reference inside it continues to mean what it meant. And so we made some variable C that was in this area. Well, the C inside count always referred to that one, even when count was being called somewhere else. And I skipped it because it's a straightforward explanation that everybody expects, and it's the way things are. But that's what static versus dynamic scope is. And so, yeah, all that stuff works as expected. Okay. Well, I don't think I want to dive into a new topic in the last few minutes, so if nobody's got any questions, I think we'll just call it good.
Did you cover the section on closure in your notes?
Closure?
The binding?
Oh, no, I skipped that one. I said
Okay.
as I was going, it wasn't real relevant to see
All
us
right.
do it.
Okay. You want to edit your notes then and remove it if we're reviewing later? Then we don't have to.
Oh, sure.
What's due on Monday? Is it this class or 440?
That'd be 440.
Okay.
Yeah.
Was last one for this class, you said at the end of the day, would that mean like tonight, or what do you mean by end of the day for?
It means I'll try and grade it tomorrow.
Okay.
Do you have any comments about the programming language Swift?
No, I haven't used it, so no.
Okay.
It looks really weird.
It says that it's for like Apple, and it's helpful for like Object-C and Object-C++, but on a Wikipedia.
Yeah, they intend to replace both high and low level languages with it.
Ah.
It's like Apple's version of Go.
Yeah, kind of. And it might be kind of a neat language. I never used it, so I don't have any comment.
They're using it a lot for the games, like for app games and stuff on iPads and such.
Yeah, because Xcode is the new upper level shell or coding for Xcode, isn't it? Or Objective-C.
Yeah, but that's been around for a while.
Yeah, but they didn't include it in the Xcode IDE until just recently, I think.
Yeah, it's yeah.
Can you take a look?
Python's been okay.
Is this part of Bitwise?
Yeah.
Did you see the
funny comment that I